All right, let's take a look at how to do these relative motion problems. There's no general equation for them, so it's important that we have all of the subscripts listed correctly and that we're nice and neat when we're listing everything out. So both problems have to do with boats. In the first one, we have a slow boat. So the velocity of the slow boat with respect to Earth is 45 kilometers per hour. And we have a fast boat with respect to Earth that's moving at 55 kilometers per hour. And we want to find out what is the velocity of the fast boat with respect to the slow boat. And I think that we already know the answer is going to be 10 kilometers per hour, but we're just going to prove that. And so what we do is we use our subscripts to show what those velocities are relative to our frame of reference. Okay? And so what we want to do is we want to find out what is the velocity of the fast boat with respect to the slow boat. And so the way that we write our equation for this is they're going in the same straight line, so we don't have to worry about angles for this one. And whatever our whatever our subscripts are here, that's the same order that we need over here. So I have F and S, so I need F like this and S like this. And the common reference point, you can see if we look back over here when we list, is the Earth. And so what we do is we need the common reference point kind of facing each other, right? So this right here, these are the common reference points. All right, let's make that a little bit thicker. So these here are the common reference points, these two, Earth. And we want those common reference point to be facing inward towards each other. Okay? And that will be the equation that we use for the most part. Now, what we do have to do for this, though, is if we have to go back and check and look. So if I have everything listed here, right, I've got fast boat with respect to Earth, so I've got that one. But here I've got Earth with respect to the slow boat. So I don't have that one exactly here. So what I need to do is I need to reverse this. And the way that we reverse this is we just add the opposite. So then for this problem, the velocity of the fast boat with respect to the slow boat, this one is fine. Fast boat with respect to Earth is good. But we have to add the opposite of what we were given because these subscripts here are reversed from over here. So this means it'll be the opposite of the fast boat of the velocity of the slow boat with respect to the Earth. So this becomes the equation that we use for this problem. If we put all the numbers in now, we've got our fast boat with respect to Earth, which is 55 kilometers per hour, plus we have to add the opposite of the slow boat, so negative, that didn't come out very good, negative 45 kilometers per hour, and we can see that the answer clearly is going to be 10 kilometers per hour. And I think that we knew that was the case, but for this problem we just proved that that was the case. For our next problem, number 2, we've got a boat that's traveling eastward across a river, and the river is flowing southward at 8 kilometers per hour. So we've got the velocity of the boat with respect to the water, and this will be our 5 kilometers per hour, and this is to the east. And then we have the velocity of the water with respect to the Earth. This is the flow of the river, 8 kilometers per hour, and this one's to the south. We want to find out what is the velocity of the boat with respect to the Earth. So if we have like a little picture over here, here's the boat. The boat's traveling in this direction. This is the velocity of the boat with respect to the water, right? Here's our river, like this. And the river is flowing downward this way, right? So that's the velocity of the water with respect to the Earth. And I think you can see from our picture right here that we have a right triangle, right? We've got east in this direction, we've got south in this direction. And so what we can do then is just use a right triangle to find this. So if I draw my vectors again, This would be the velocity of the boat with respect to the water. This would be the velocity of the water with respect to the earth. And all I want to do now is add those together. This would be the velocity of the boat with respect to the earth, and that's what we want to find. And of course, we also need the angle that's here. So because this is a right triangle, all we need to do is use Pythagorean theorem. So if I want the velocity of the boat with respect to the earth, it would just be the square root of both of these together. So the velocity of the boat with respect to the water squared plus the velocity of the water with respect to the earth squared. And then I take the square root. And you can see from this, I still have my common reference points. Right? I've got the water and the water. So it still works out. It still fits perfectly. And we don't have to do anything else to this equation. This will give us the magnitude of that velocity. Let's put the numbers in. So velocity of the boat with respect to Earth will be the square root of, we've got our 5 kilometers per hour squared plus our 8 kilometers per hour squared. And then the calculator does all the work for us, and this gives us 9.4. Oops. So that would be the magnitude of our velocity. If I want to find out what the angle is, I'll use my inverse tangent. The opposite side would be the velocity of the water with respect to Earth. The adjacent side is the velocity of the boat with respect to the water. So we put our numbers in here. Inverse tangent, our 5 kilometers per hour, divided by our 8 kilometers per hour. And this gives me 32 degrees. So then the final answer for this, the velocity of the boat with respect to Earth, is going to be 9.4 kilometers per hour at 32 degrees south of east. So when we do our relative motion problems, we're not really doing anything new. We're just adding a little bit more detail to everything that we've already done with the way that we've adding vectors in the past. I'll see you in class.